Hi everyone, in this video we're looking at measures of spread, including the range and standard deviation. So I'm going to start with just a small data set here. We have ages of some people in a small class, so 19, 20, 20, 21, and 28 are the ages of the people. So the most straightforward measure of spread, meaning how spread out are our data values kind of on a number line, is the range. And the range is just the max value minus the min value. In this case, the max is 28 years, the min is 19 years, and so that range is 9 years. So that's just telling us that from the oldest person to the smallest person is a difference of 9 years. Now the range is pretty easy to calculate and gives us a good idea of the spread of those max and min values, but if either our max or our min is an outlier, for example, maybe the oldest person in this class is 38, that's going to result in a much larger range because we're only looking at that max and min value. So the drawback to range is that it doesn't really tell us about any of the values in the middle. In this case, most of the ages are around 20, so 19, 20, 20, 21. Most of them are pretty close together. It really is just this one or upper value that is significantly further away. So we're getting a very large range, even though most of our data in this case is pretty close together. If I look at a real data set, so this is one I've featured in previous videos, this is MMR immunization rates at different schools in Colorado. Looking at the histogram, we see that most of the bars are towards the right-hand side, around 80, 90, and 100%, and that's the majority of the frequency. But there are some bars out towards the left, all the way down to 0% fully immunized, even though we can't really see the heights of those bars. I'm going to switch over to the data. So here is that percentage immunized for these different schools. And if I want to compute the range in Excel, I need to find the min value and the max value. So for min, I use the function equals min parentheses, and then I'm going to put my data values in here. So in this case, I have a really long list. I'm going to click the K, or the letter above that column containing all my data. That highlights the entire column, and then I close my parentheses and press enter. So the min value of all of these percentages is 0, and the max I'm going to do equals max parentheses, then highlight that whole column of data, clicking the K above the label, and my parentheses, press enter. The max value is 100. So we have percentages in this case from 0 up to 100. The range here would be 100, but I would be calculating that with equals, and then I can click on the box containing my max, minus, click on the box containing my min, or just do 100 minus 0 in this case. So the range of values is 100%, but this doesn't really represent the general spread of most schools. Most of the schools have percentages, visually speaking, we're seeing the bulk of the data between about 80% and 100%. The next measure of spread is called the standard deviation, and the standard deviation is essentially going to look at each age or each data value on its own and ask how far away is that data value from the center. And the center we're going to be using is the mean. So how far away from the mean is 19, how far away from the mean is 20, 20, 21, 26, etc. And then we essentially average those together in a certain way to see the average spread or the average deviation from the mean. So here's what the calculation looks like. We're going to start by taking each one of these ages or each one of these data values and finding what's called the deviation. The formula for this looks like x minus x bar. That means the data value, so one particular age in this case, minus the mean. The mean of this data set is 21.2. I calculated that in a previous video. That's just all of these numbers added together divided by 5. So I'm going to take 19 minus 21.2. That gives me negative 2.2. That's indicating that the person who is 19 years old is 2.2 years younger or less than the mean. And then 20 minus 21.2, another 20 minus 21.2, 21 minus 21.2, 26 minus 21.2. So each one of these data values from the list minus the mean, this gives us our deviations. So we have deviations of negative 2.2, negative 1.2, negative 1.2, negative 0.2, and 4.8 in my little list here. So once I've calculated all of those deviations, I can't directly average these, because if I found, for example, the mean of all of these deviations, I would actually just get 0, because there's sort of an equal amount above as below in terms of an average. So what we do is we square each deviation. So I have here this deviation squared, x minus x bar quantity squared. So I'm taking each of those previous numbers, negative 2.2 was the first one, and I'm squaring them. Now by squaring them, we do change the size of the number, and we also make it positive. So 4.84, 1.44, 1.44, 0.04, and 23.04 are the squares of each of these numbers in the deviation column here. Once I have each of those deviations squared, we are going to add them all up. The notation for this is using the Greek letter sigma, capital sigma, that represents a sum. So we're taking the sum of all the deviations squared. So I took each number from that deviation squared column, added them all up. In this case, that total is 30.8. So the sum of the deviations squared. Now we're going to average this. If you look at the formula in our textbook or online, what we're looking at is the sum of the deviations squared divided by, in most cases, we're going to use an n minus 1. Now, in a typical average, we would just use n, meaning the number of data values. N in this case is 5. But for sample standard deviation, and I'm assuming that this is a sample of ages here, we actually divide by 1 less than this. And this is a correction that allows the sample standard deviation to be a better approximation of what the true population standard deviation would be. In most cases, we are dealing with sample data, so you will typically use this version of the formula. But if you had a population of values, if this was the whole population, we would use the population version of this formula, which has not n minus 1, but just an n. If that was the case in this data set, I would use divided by 5 here and get a slightly different number. But I'm going to stick with the sample calculation here. So I'm taking that sum of the deviation squared divided by n minus 1, or in this case 30.8 divided by 4. That gives me 7.7. Now the very last step in the formula is to take a square root. So this right here that I'm seeing is the formula for the sample standard deviation. This is the square root of the sum of x minus x bar squared divided by n minus 1. So we do this in terms of order of operations, first by doing x minus x bar, then by squaring each of those values, then by adding them up in the sum, then by dividing by n minus 1, and finally by taking the square root. So I'm taking the square root of that previous number, the 7.7, and I get a long decimal that I round to, in this case, 1 decimal place, since our original data has just whole numbers. I rounded this to 2.8. Now, by taking the square root, we're kind of undoing the squaring that we did in this previous step, and that kind of rescales the differences back down to their normal size. So what exactly is the standard deviation giving us? We can think of this as sort of the average deviation of data values in the data set. So for these people in this small class, their ages differ from the mean by, on average, 2.8 years. Now, some of these ages are obviously further from the mean and some are closer to the mean. None of them actually equal the mean in this case, but some of them are quite close, like the 21 here is very close to the mean. And some are further away, like the 26 was almost 5 years away from the mean. But when we average all those deviations together, we get this 2.8 years. So that's kind of the typical or average deviation from the center. I'm going to switch back over to my real-world data set. So we were looking at these immunization rates at Colorado schools. We found that the range was quite broad, from all the way from 0% immunized up to 100% immunized. But let's look at the standard deviation. So as you can imagine, this data set, which actually has hundreds, if not thousands, of schools in it, finding the standard deviation in that same method where we're taking each value minus the mean, squaring the difference, and so on, would be incredibly tedious. Now, you could do that using some Excel formula tricks, but Excel actually has a standard deviation formula built into it. So I'm going to use my equal sign here, and the formula looks like STDEV, short for standard deviation. And if you type that in, you'll see that there are a few different suggestions here. The first one is stdev.p. That .p represents population. So if this is a population, which in this case it actually is, we have all of the different schools in Colorado, not just a sample, I can use this .p version. If I do have sample data, I would use the second option, stdev.s. The only difference between these two was that either we're dividing by the n-1 or the n in that formula. Because this is a large data set, they aren't going to be very different because n is quite large. But I am actually going to choose the .p in this case. But in most cases, the data that we're dealing with is a sample. So in most cases, you're going to use the .s formula. Other than that difference, they work the exact same way. Once you type in your formula, you do your parentheses to open up the parentheses, and then highlight your data values. I'm clicking on the K above my column again to get the whole list. Close my parentheses and press enter. And ta-da, we have a standard deviation. If I did the sample version, equals stdev.s with the same numbers, I get almost the same number. This is just a slightly bigger number for the sample version. But in this case, because this is the percentages from every single school in the state of Colorado, I'm going to stick with the population version. The interpretation would be the same here. This is saying that if you consider all the schools in Colorado, these MMR vaccine rates vary from the average. The mean is 91% up here. They vary from the average by about 11 or 12%. The units on standard deviation and the range are both the same units as the original data values. So while the range is 100%, the standard deviation is 11 or 12%. And this gives us a sense of the spread of the data. We could use this to characterize values as sort of typical or atypical, identify outliers and things like that. You'll see more of what you can do with the standard deviation when you talk about z-scores later in the section. But this is, again, giving us this measure of spread. That's it for this video. Thanks for watching.